What's up, mathematicians? Justin here, and welcome back. Today we will be starting a brand new unit. This will be unit number 5 about tiling. Now we'll find out more about what tiling is, what that means as we go through the unit. Today we will be doing lesson number 1 in this new unit. Lesson number 1 is the angle sum of a polygon. Did you think I was going to say angle sum of a triangle? I bet maybe you did, because I've been saying it a lot in the last, over the last few lessons, last number of lessons. But no, today we will be using the angle sum of a triangle. We'll be building on that to figure out how we could find the angle sum of any general polygon. Now, before we get into the lesson, let's take just a minute to think about where we're at, okay? So going back to unit number 1, it was about measurement, and in that unit, we made some assumptions as we built up these tools for measurement. But then we thought about it and we thought, how do we know these things are true? Could we prove them? And then we spent a lot of time, really all of the previous 2 units, building up this beautiful, shiny axiomatic system, right? Where we started by coming up with some rules and some assumptions, and then from that foundation of rules and assumptions, we built up, we proved these bricks, these theorems, and we worked our way up to these big ones at the top, these that we needed for our measurement tools. Okay, now you probably can't read this, so let's take a closer look at those here for just a moment. And these are the big ones that we proved in the previous units, right? So first of all, we proved that the angle sum of any triangle is 180 degrees. Important for some of those measurement tools, including trigonometry, right? We also proved that squares exist and we can construct them. That is something we need for area, right? Because we measure area in square units. And if squares don't exist, how can we have square units? Also, we proved that the Pythagorean Theorem is true, another useful measurement tool, and probably the most famous theorem in all of geometry. And finally, this last one here, that similar triangles exist and their sides are proportional. This, it turns out, is really important for different measurement tools, including those trig functions, sine, cosine, and tangent. They all rely on this similar triangles theorem. Okay, so this is great, by the way, because our unit on measurement relied on all these things, these tools for measurement. So awesome. Now in this unit, we will build on the fact that the angle sum of a triangle is 180 degrees to learn a bit more about other polygons and the ways in which polygons can tile our surface. So in the process of proving the construction of the square, we had to prove that the angle sum of any quadrilateral is 360 degrees. But what about polygons with more sides? What about pentagons or hexagons or dodecagons or 473 gons? What would the angle sums of those shapes be? Okay, so we will address that question in this lesson. However, before we get started, let's go over a few definitions. I'd like to define a few things for you now. Okay, so before I share these definitions with you, I would actually encourage you to pause the video and write down what you think the definitions are. This will help you to remember the definitions better in the future. And the definitions that we'll be talking about are definition of polygon, definition of concave and convex polygon, and definition of regular polygon. So take a minute and write down what you think those terms mean. Polygon, concave and convex polygon, and regular polygon. Pause the video and write your ideas down. Okay, so now let's talk about what those terms mean. First, let's start with the polygon, okay? And we actually defined this in our axiomatic system, but just to go ahead and talk about it again, I'll make sure we're on the same page here. A polygon is a figure on a surface, like this dot grid sheet of paper, and it is made up of lines meeting at their endpoints. Okay, now I'm not going to say that this is a complete and rigorous definition, but it should be good enough for our uses. So some examples of polygons are these, right? We have a triangle over here, we have a quadrilateral over here, and this might feel like a little weird to say this is a polygon, but it is made up of lines meeting at their endpoints, right? So this fits the definition. And this would actually be, I believe, a hexagon, right? Because we have 1, 2, 3, 4, 5, 6 sides. So this is a hexagon, even if it's not what you would necessarily think of when you think of a hexagon in your mind. Now, some non-examples are over here. This is made up of straight lines, but we don't see the lines meeting at their endpoints right here. So this is not a polygon. And this one here has one straight line and one curved line. So again, not a polygon. So one that I thought I would talk about for just a minute here, because sometimes people get a little confused about this. So suppose that I drew 3 lines like this. People might look at this and say, that's not a polygon because it's not made up of straight lines meeting at their endpoints. Well, it turns out that if we look at this, there is a polygon here, right? There's a polygon. The 3 lines do actually make a polygon. They make a triangle. And we can see that this triangle right here is made by those 3 lines. Now, the parts of the lines that go beyond the vertices, yeah, I wouldn't say that those are parts of a polygon, but there certainly is a polygon right here. And one other that we should mention, and let's see, I'll put this in maybe an orange color, is the following. Okay, so imagine I drew this. And here, and then I connected it like this. Would that be considered a polygon? Well, on one hand, you could say, well, okay, there are 2 triangles there, so it's 2 polygons. But think of it as a potential quadrilateral, right? A 4-sided figure. And it's made of 1, 2, 3, 4 lines. They all meet at their endpoints. So is this a quadrilateral? Well, we would call this a degenerate quadrilateral, okay? So this is a degenerate quadrilateral. I'll just abbreviate it as quad, okay? And so in this unit, we are going to go ahead and just ignore degenerates. Now, technically, we could say they fit the definition, but we will ignore them. And that's one thing to think about with these definitions is this fully rigorous? Probably not. But I just wanted to point out that we are going to go ahead and ignore or exclude degenerate polygons like this one, where the lines cross over each other. Now let's talk about concave and convex polygons. So here on the paper, you see 2 pentagons. This one is concave and this one is convex. What does that mean? Well, in a concave polygon, it is possible to find 2 points such that when you connect them with a line, that line is at least in part outside the polygon. So let's show how that would happen here. So if I put a point here and I put another point here and I connected those 2 points with a line, we see right there, that line is in part outside the polygon. Part of it is not in the interior of the polygon. And so this is a concave polygon. Now, in a convex polygon, any 2 points I pick, if I connect those 2 points with a line, that line will always be completely inside in the interior of the polygon. So let's say I pick a point, I'll try to pick one close to the edge, and I pick one here. It doesn't really matter where I pick the other one. I'll pick one over there, and I connect these 2 points with a line, and I see that line is completely inside the polygon, and there are no 2 points that I can pick such that if I connect those 2 points with a line, it will at some point leave the interior of the polygon. So that is concave and convex. And finally, let's talk about what a regular polygon is. So a regular polygon is a polygon in which all the sides and all the angles are equal. So I have drawn here a hexagon. Now, I clearly did not draw this perfectly as a regular hexagon, but if I had, it would be the case that all these 6 sides would be equal and all the 6 angles would be equal to each other. Okay, so again, my drawing is not perfect, but if it were a perfect regular hexagon, that would be true that all the sides and all the angles would be equal. Now I'd like you to pause the video and take a minute to go through the argument that any quadrilateral will have an angle sum of 360 degrees. As you go through this argument, consider both convex and concave quadrilaterals. Take a minute to go through that argument on your own. Okay, so here are 2 quadrilaterals. One is convex, one is concave. And if we wanted to convince ourselves that these quadrilaterals both have an angle sum of 360 degrees, what we could do is we could just draw a diagonal connecting the 2 vertices on each one. Now in this first one, it doesn't really matter where I draw the diagonal. I could draw it between these 2 vertices, or I could draw it between these 2 vertices. But when you draw this, you want to make sure that the diagonal does go through only the interior of the polygon. So go ahead and draw it there, and I see I have 2 triangles. Now I know that the angle sum of these 3 angles here is 180 degrees. I also know the angle sum of these 3 angles here is 180 degrees. That's because we've proven the angle sum of any triangle is 180 degrees. So if we look at the quadrilateral, well, all these angles together make up all the angles of the quadrilateral. And so the angle sum of the quadrilateral must be 360 degrees. So there it is for a convex one. Let's look at the concave one. Now, when I make a diagonal, I don't want to draw it here. That would make my argument a bit more complicated. Let's keep it simple. And let's go ahead and draw the diagonal right here. Once again, you'll notice that this quadrilateral has now been divided into 2 triangles. And once again, each of these triangles will have an angle sum of 180 degrees. And therefore, the quadrilateral will have an angle sum of 360 degrees. So in this unit, I will be focusing more on convex quadrilaterals because, that's what ends up being more useful for what we're doing, okay? And so I do want to just point out or mention that when I say polygon, unless I particularly specify that it's concave, I will actually be referring to a convex polygon. And one other thing, in this unit, I actually would like to refer to quadrilaterals as tetragons because it just makes sense, right? I mean, seriously, a 4-sided polygon should be called a tetragon. A 3-sided polygon, for that matter, or a triangle, should really be called a trigon. And 2-sided polygons, well, they should be called bigons. And because 2-sided polygons don't exist, we can just let bygones be bygones, can't we? Anyway, now let's consider how we could determine the angle sums of polygons with more than 4 sides. We know that a polygon or a tetragon, right, with 4 sides is going to have an angle sum of 360 degrees. So recall that we just proved that a minute ago. So now I'd like you to take a little time to figure out what is the angle sum of a pentagon? What is the angle sum of a hexagon? Do you see a pattern as you figure these angle sums out? Do you think that this pattern will continue? How do you know? Can you prove it? And so once you've done that, you've figured out the angle sum of a pentagon and a hexagon, I'd like you to come up with a method for determining the angle sum of any polygon. Can you come up with that method and find a formula that corresponds with that method that you came up with? By the way, there is more than one way to do this, more than one way to correctly come up with a method and a formula. And so if you have a little time and you've already come up with one, try to find a second one before watching the next video. Okay, so just to recap, here are a few things that I'd like you to try to do yourself on your own before you watch the next video, okay? So number one, find the angle sum of a pentagon and a hexagon. Number two, look for a pattern in the angle sums. You know the angle sum of a triangle, you know the angle sum of a tetragon. Remember what a tetragon is? And once you find these, do you see a pattern in those angle sums? Then create a method, a technique for finding the angle sum of a polygon with any number of sides. And once you have a method, find a formula that corresponds to that method and try to prove that the formula is in fact correct, okay? So those are a few tasks for you to go work on. That will wrap up this video. And in the next video, we'll look at a couple different ways to find the angle sum of a polygon. See you then.